Hi everyone, my name is Sundar Ganesh. I am a PhD student at APFL under the guidance of Professor Fabio Nobile. I will be speaking today on the efficient multi-level Monte Carlo estimation of risk measures that are important to risk-averse engineering design. So this is a combined work with my colleague Quentin Ayul-Kelmar, who's a postdoc at APFL, and with Sebastian Krumscheid, who is a junior professor at the RWTH in Aachen, Germany. So let's begin. This work is part of the EU Horizon 2020 project Execute. The aim of the project is to enable robust shape optimization in civil engineering by leveraging design parameters of buildings such as twist angles or number of towers, etc. And the aim is to design these buildings in a way that's robust to wind uncertainties. So the way to we require a way in which to quantify these uncertainties, and we look at certain categories of risk measures. So the first one is commonly used, which is called the mean variance risk measure. However, we aim to study more tail statistics in some sense, and so we look at measures such as the value at risk or the quantile, or the conditional value at risk, which has properties that are favorable to gradient-based optimization techniques. So immediately off the bat, the problem has some characteristics favorable to the use of MLMC methods. The first one is that wind uncertainties are typically high dimensional, and so this motivates the Monte Carlo part, and the underlying PDE, which is usually some version of Navier-Stokes, is high cost to solve, and so multi-level methods have shown promise in basically hiding the cost of solving the PDE. Some challenges will be faced and will be addressed in this regard. The first is that we need to design MLMC estimators for these exotic statistics like the VAR and the C-bar. On top of which, we also need accurate and efficient error estimators for these estimators, because we'd like to use as few computational resources as possible to achieve a certain tolerance on these estimations. Lastly, we'll need MLMC algorithms to calibrate these estimators and to estimate appropriately the required rates and constants, etc. So the structure of the talk is going to be as follows. First, I'll give you a brief overview of MLMC methods. Then I speak about MLMC for parametric expectations and for and the corresponding error estimation techniques. I then go on to adaptive strategies for how to tune the MLMC hierarchies parameters. And then I present a couple of numerical studies. The first one is for a toy problem, and the second is for a little more applied problem. Then I conclude with some future goals. So on to MLMC. So let's do some terminology. So first, omega FP is a probability space. Small omega denotes a random elementary event, and Q of omega denotes a quantity of interest, which is typically a functional of the solution of an underlying PDE. And the broad goal of this is to estimate somehow statistics of this quantity of interest. The idea behind MLMC is to approximate the underlying QI on a sequence of approximation parameters. And the first thing that of course comes to mind is to use a sequence of meshes of geometrically decreasing mesh sizes. There are other candidates such as time step sizes or the number of basis coefficients, but for the purposes of the study, we look at mesh parameters. So I present here the MLMC estimator for the expected value, although the one for higher level moments follows a similar structure. So you use the linearity of the expected value to rewrite the expected value on the finest level as this telescoping sum. And then you replace each of these expectations with a simple sample average to give this particular form of the estimator. An important thing to notice is that when you're estimating this expectation, you solve the underlying problem on both levels using the same underlying realization. And so what MLMC does is basically to exploit these correlations to somehow reduce the cost. Now, the mean square error on this estimator, defined in this sense over here, splits neatly into two terms. The first one is the error that you make due to discretization, and the second one is the error that you make due to sampling, so a bias error and a statistical error. A few theorems have been presented in the past before about complexity, and both for the expected value and for higher order moments. But the basic idea goes like this. So if the bias error, the variance, and the cost decay and grow exponentially with the levels with these rates alpha, beta, and gamma, then there exists a cost optimal way in which you can pick the number of samples and the maximum level for a given tolerance epsilon, such that the net cost of the MLMC estimator grows like this with the tolerance. So in the best case, you can see that you recover the Monte Carlo tolerance. What this basically means is that the simulation doesn't see the cost of solving the PD, and that the cost is dominated by solves on the coarsest levels. And in the worst case, you can see that this is already an improvement over a comparable Monte Carlo at the finest level. So that motivates MLMC. Then we move on to the introduction of parametric expectations. So parametric expectations are expectations of this form, where you compute the expected value of a function which is on a certain domain and takes q as a sort of random input to produce this function capital phi. I use the superscript notation for derivatives, and we look at estimating this function capital phi on a domain capital theta. For the rest of this work, we focus on this particular form of the function small phi, uh, where q and theta have been introduced, and tau is basically the significance of the statistic that you want to compute. The reason that we use this form is that you can, if you estimate the result in capital phi, then you have all of these statistics available for free by just post-processing the function in a simple way. And we'll see in a bit that this also has quite some favorable statistics in terms properties in terms of decay rates. So on to MLMC. How do you estimate this function using MLMC? Well, so we propose estimating this function pointwise on a set of points theta 1 to theta n on this domain capital theta, and then we interpolate with the cubic spline. Once again, as before with this capital phi, we rewrite the expectation in this telescoping sum form, and then estimate each of the terms using a finite sample average. And so this gives you this capital phi evaluated at each of these points. Once you have this, you can interpolate using this interpolation operator Sn, and compute derivatives as required of the resultant spline to get the final function estimate. Now, immediately, this has some implications. So the first one is that small phi is Lipschitz in Q, which means it's bounded by the difference between levels for small phi is bounded by the difference between levels for the QI itself. And this means we can make the same kind of rate hypotheses as before, and we can expect some optimal complexity behavior as well. Another is that in combination with spline properties, we can go from the mean square error on this function derivative to the mean square error pointwise in small phi on this domain. And so this gives the ability to compute error estimates. We define the mean square error in this L infinity sense. And if you use a triangle inequality with weights A1, A2, and A3, you can see you can work out that it neatly splits into three contributions: the interpolation, bias, and statistical error. Where this one is new right now because of the spline interpolation. We'd like to relate this mean square error to pointwise error estimates on the function. And so following this work, what we do is, so I present here the final forms of each of the error estimators. We find the a priori estimate for interpolation error to be satisfactory. However, bias and variance, as you can see, they have a particular issue. So which is that the leading constants can get extremely large. By writing them in this form, however, we can see that we can use this Lipschitz property, and we can expect some kind of decay rates with optimal decay rates with both the bias and the variance, where we recover the decay rates on the QOI. However, the resultant inverse inequalities that we used to get here leave us with very large leading constants. If you use these to predict the number of samples and levels, you get huge, unrealistic, non-practical hierarchies. So the main challenge of this work is to tackle that, and we present ways in which we can solve this problem. So the first term that we tackle is the bias term. And the problem basically goes like this. So if you want to estimate capital phi as expected value of small phi, and small phi is piecewise linear, then replacing the expected value with finite number of samples is basically a linear combination of piecewise of piecewise linear functions. And so capital phi is piecewise linear, the first derivative is piecewise constant, and the second derivative doesn't exist. And so this regularity issue causes problems with getting the optimal decay rates. Now, since the problem is with using the empirical measure or using finite sampling, we expect the problem to go away if we smoothen the measure with the Gaussian KDE. So basically, we take this expected value, write it out in this integral form, and replace the density with the 2D KDE that's centered on the correlated samples that we've generated at level L. And so since we know that this is Gaussian and we know this is this piecewise linear form, this has a closed form expression. Once we have the closed form expression, we can simply generate point values, interpolate, and compute derivatives to compute bias estimates at level L. We find that by doing this, we get optimal rates. And so I present those results here. So these are plots with the bias on the y-axis and the levels on the x-axis. This is basically bias versus levels for a screening hierarchy where we run 5 levels with 100 samples per level. The plots from left to right are basically to estimate the function derivative, and the function's second derivative. There are two things to notice here. The first is that the red line denotes the naive a priori estimates with the huge constants. And you can see that as derivative order increases, this distance grows massive, and basically, although it recovers good rates, the constant is way too large. And ideally, I think we're supposed to, so the underlying PDE here is a Poisson problem. So we recover rate 2 in the levels. The naive estimates, you can see the rates get progressively worse with higher derivatives, and to the extent that you don't recover decay over here. So we find the KDE's performance superior to the naive performance, and with fewer samples, you see that the KDE very easily outperforms the naive way of estimating these function derivatives directly using the empirical measure. Now onto the statistical error. So to get the statistical error, we use bootstrapping, and the way that we do this is that let's say you have this calligraphic Q which denotes the current hierarchy with the correlated pairs at each level. The idea is to create NBS hierarchies of the same size, where at each level you pick the same number of samples as the original hierarchy by replacement. Then you can basically, now that you have NBS hierarchies, you can compute NBS estimates of the function. And once you have these bootstrapped estimates of the function here denoted psi j, you can simply take the expression for the statistical error and replace both the expectations with sample averages. And this gives you an estimate of the statistical error, which we denote by SEBS. And so we find that this provides satisfactory statistical error estimates. Lastly, now we have all of the ingredients for estimating the mean square error on the function derivative. How do we relate the mean square error on the var and the c var to mean square error on this function? So let q tau denote the true var and q tau hat denote the var estimate. And so here we present the results for var, but similar results exist for the c var as well. And you can show that basically in expected value, this can be bounded by constant times the mean squared error on the function's first derivative. And the proof is related to Taylor's theorem, which is basically to say that the error on the y-axis is equal to slope times the error on the x-axis in some sense. In practice, though, for estimating this constant, instead of actually looking for the L infinity norm on this interval, we just evaluate this second derivative at the current quantile estimate, since we expect the quantile estimate to be close to the quantile and this interval to be small. We find this to be satisfactory in practice. That concludes the error estimation section. Now we move on to the adaptive strategy. So for the adaptive strategy, you can basically relate. So we present here the adaptive strategy for the var. Now the mean square error on the var can be bounded by doing this, where we use a triangle inequality and this leading constant to say that the mean square error on the var is equal to some leading factor times the mean square error on the function derivative. We then, so for the mean square error on the var to satisfy a tolerance epsilon square, we split the contributions from each of these terms with weights W1, W2, and W3, and we require each of these individual contributions to satisfy these inequalities, which ensures a tolerance epsilon square on the mean square error on the var. For the number of interpolation points, we found the a priori estimate to be satisfactory. So this is the expression for the a priori estimate. By requiring this to be less than tolerance, given that the expression is dependent on the number of interpolation points, you just invert it and you get this. There is this this issue of computing the fourth derivative of the function, and so we expect regularity issues to crop up here as well. However, if we use a KDE approach to smoothen this expectation as well, the problem goes away and you have the number of interpolation points. For the bias, we first note that you can take the bias in this particular form and rewrite it as a telescoping summation, right? Now, once you, so from level L all the way to level infinity, which is the true function in some sense. We then expect this to decay at a certain rate, since we've now smoothened the bias. And so we fit an exponential model on these KDE smoothened estimates. And so this model gives you a particular form for the bias at level capital L. And so you can pick capital L such that the bias satisfies a certain tolerance. Then for the number of samples, there's two issues here. So the first question is how to localize this variance contribution to each level, because you need to know which level contributes how much variance to the total statistical error so that you can tune each level's number of samples appropriately. And so we saw earlier that the a priori estimates used in inverse inequalities to get to this particular form, but that the leading constants were large. So you could get it to this pointwise form, which I denote this term as VL, but the constants were quite bad. So we propose rescaling the variances VL such that the total adds up to the bootstrap statistical error that we computed earlier. So this is how we propose to localize the variances. Once we have that, then it's quite straightforward. You basically select the number of samples to minimize this multi-level Monte Carlo cost, where CL is the cost of solving the quantity of interest on level L, such that this quantity satisfies a tolerance. And so this gives you a straightforward expression for the optimal number of samples. So here I present two ways of computing the variance. It's the same as before. Y-axis is the variance and x-axis is the levels. The red line denotes the rescaled variances that we described in the previous section. And the blue line denotes basically this naive way of computing it, where you can use an inverse inequality to write it pointwise in terms of the derivatives of small phi instead of just small phi. And so you can see that this rescaling method drastically outperforms the naive way of computing it for all three derivatives, both in raised and constant. So lastly, the last ingredient is the MLMC algorithm. So I present here the CMLMC algorithm, which basically uses a sequence of tolerances, of which the target tolerance is the last one. You start off with a small hierarchy, and you don't want to commit yet to optimizing the hierarchy based on the final tolerance, because you could have bad estimates in the first few samples. As a result, you use this decreasing sequence to somehow adapt your hierarchy iteratively, and so by the time you reach the final tolerance, you're fairly sure of your estimates. And so the additional caveat is that once you reach the final tolerance, if you still don't satisfy the error, you refine a few more times, and this gives you a hierarchy that satisfies your error criterion. Good. So this is a summary of all of the methodology. I present two problems. The first one is the 2D Poisson square on a square domain with Dirichlet boundary conditions. We pick the source term to be of this form with some constant k times a random variable xi times this function. Uh, we uh, we look at the quantity of interest, which is the integral of this field over the domain of interest, and we know that this has a closed form expression as follows. We've chosen xi to be a beta random variable with parameters 2 and 6 for the mean and variance, and so we know exactly what the quantile is supposed to be for this quantity of interest. I present here what's known as a reliability simulation. So the y-axis is squared errors and the x-axis is tolerance. So what we do is run the entire CMLMC simulation multiple times. So each time a simulation is run, it produces an error estimate and it produces an estimate of the var. So since we know the true var, we can compute the true error and compare it to the corresponding error estimate. And so the red dots denote the error estimates and the green dots denote the true estimates. Each dot corresponds to one entire run of the CMLMC, and each vertical set of dots corresponds to one final tolerance. And so we find basically that this produces practically computable hierarchies and fairly tight error bounds. The second problem is more applied. It's Navier-Stokes incompressible equations with incompressible steady equations, where with a low Reynolds number. The problem is flow around a cylinder, so we pick the Reynolds number to be 10 to ensure that we get steady solutions. The problem is discretized with P1, P2 finite elements on a sequence of meshes where the mesh parameter used to generate the mesh is refined by square root 2 for each level. The quantity of interest that we look at is the drag force, and we compute this by integrating the asymmetric stress over the surface of the cylinder. For the inlet uncertainties, we propose this form where we have the parabolic profile as usual, but we add on to it certain random sinusoidal terms with the two components in their amplitude factors. So the first component is an exponentially decreasing factor with an initial step, and the second is a standard normal generated random variables, and we do this to somehow simulate higher dimensional uncertainties. The black line here denotes the parabolic profile, and the multiple colored lines denote different realizations. Here is the resultant reliability plot. We compute the true var estimate for this simulation using a reference simulation with 10,000 samples on a really fine mesh. And here as well, we find that a computable number of samples and levels is proposed by the hierarchy optimization. However, we still seem to not. So we see that it's not as tight as for the Poisson problem. And currently, we're still investigating this and seeing if there's a source of error that we can somehow even further optimize. Yeah. So good, that brings me to the end of the talk. So in the future, we want to expand this to error estimators for the conditional value at risk. We expect the same framework to hold except for this prefactor to go from the error on the statistic to error on the function derivative. The second is that it's critically important to recover the optimal decay rates. One component of this is, of course, rewriting the formulation to the pointwise estimates, but another critical formulation is using adaptive mesh refinement for more applied problems to capture their optimal decay rates with mesh parameters. And of course, this is easier said than done for Navier-Stokes. The third is we're going to also be looking at time-dependent problems. So somehow we have to come up with and study notions of var and cvar in time, and this ties together with with another topic, which is MLMC for time-dependent problems. Lastly, the grand aim of the project is, of course, optimization, and so we aim to extend this framework through sensitivity estimation as well using MLMC and an eventual combination with an optimization engine. So that brings me to the end of the talk. I would like to thank the European Union's Horizon 2020 program for enabling this research. So, thank you.